We will solve a problem, right, of column stud. Here question is calculate the maximum value of the slenderness ratio of mild steel column for which Euler's formula is valid, right? We have to check the applicability of Euler's formula. Conditions are given. Crushing stress for mild steel column is 330 megapascal given, and modulus of elasticity is 210 gigapascal, right? So we will limit the Euler's formula, right? We know that Euler's formula is applicable for long column, very long column, because when we are deriving Euler's expression, then we have made an assumption that the column should be straight and it should be a long column, right? And we know that column buckles at the stress very lower than the compressive yield stress, right? Column buckles at the stresses very lower than the compressive yield stresses. So initial condition given to us is, if crippling stress, right, या buckling stress is sigma CR, then sigma CR is less than or equal to will be compressive yield stress sigma C, right? Sigma CR where is equal to PCR upon A, right? So crippling stress will be less than or equal to crushing stress, right? Compressive yield stress, or we say it crushing stress, right? So now we know that sigma C is given 330 megapascal, and from Euler's formula, PCR is equal to pi square EI L square, right? Pi square EI L square. If we express I in terms of area and radius of gyration, then it will be pi square E AK square upon L square, right? Now simplify it further. We will simplify it further. Then it will come P CR upon A equal to pi square E, right? And take K, right? Shift K here, then expression will be L upon K square, whole square, right? If we are considering in condition that both the end of the column is hinged, right? Both end of the column is hinged, right? If both end of column is hinged, in that case effective length LE will be equal to L, right? So expression will be reduced to PCR upon A will be equal to sigma CR, and this will be pi square E upon LE upon K whole square. We know that ratio of effective length to radius of gyration is equal to the slenderness ratio, right? So this expression is showing the slenderness ratio. Clear? So this is the expression for sigma CR. Now put this value, the initial condition, say if this equation is 1, right? Here we will place the value of sigma CR and sigma C, right? So put this value into equation 1. Then what we have pi square E upon, this is LE upon K square, so we can write it lambda square, right? Or where lambda is slenderness ratio, and by this will be less than equal to, and sigma C is given 330 megapascal, so it will be equal to 330 into 10 to the power 6, right? Sigma c is 330 megapascal. So expression is now this one, pi square e upon lambda square 330 into 10 to the power 6. Clear? Now if we simplify this expression, then what will come? Value will be here, lambda square will be greater than or equal to pi square e upon 330 into 10 to the power 6, right? Put the value of e here, pi square into 210 into 10 to the power 6, and this will be 330 into 10 to the power 6, right? This is our lambda square. So here lambda will be less than equal to, when we will simplify it, then it will become 79.254. Approx it will be considered as 80. So what we see that lambda will be greater than equal to 80, right? So this is the applicability of Euler's formula. Euler's formula will be valid when, right, when slenderness ratio will be greater than or equal to 80, right? Slenderness ratio will be greater than or equal to 80, right? When the value of slenderness ratio, right, LE upon K is less than 80, so there will column Euler's formula will not give a satisfactory result, right? That's why the Rankine's formula is opted over Euler's formula when lambda is less than equal to 80, right? Now we will discuss another problem. Now here is the problem. Determine the ratio of the buckling strength of two columns of circular cross section on hollow and other solid when both are made of the same material, have same length, same cross sectional area and same end condition, right? We are going to compare a hollow section column with a solid column, right? Now initial condition is given, right? Area of cross section is same, right? Area of cross section of solid column is equal to area of cross section of hollow column. If we write the expression of area of solid section, then it will be pi by 4 ds square, and for hollow section it will be pi by 4 dh square minus d. For hollow section it will be d h square, here it is d outer square upon d minus d inner square, right? D inner square, because d internal is given d outer upon 2, d inner is given d outer upon 2. So put the value here. This is d inner is equal to 0.5 d outer, right? Here it is equal to 0.5 d outer. So expression will come out as this, they both will be cancelled out, and here ds will be equal to, right, 0.866 d outer, right? D solid will be equal to, because it will be 0.5 d outer whole square and 0.25 will be there, 1 minus 1, when we will minus that term by 1, then it will be 0.866 d outer, right? Now write the Euler formula for solid column. We are going to compare. So we know that Euler's formula for hollow column will be pH, and Euler's formula for solid column will be PS. If we write the value of these two, then here will be, right, pi square E I upon LE square for hollow one upon pi square E I upon Le square for solid one. What we find that pi square E, because they both are made of same material, so E will be same, pi is same, their in condition is same, so Le will be same. Only they differ by moment of inertia. So expression will come out P hollow upon P solid is equal to I hollow upon I solid, right? If we write the expression here, then I will be, we know that I for hollow section is equal to pi by 64 d outer to the power 4 1 minus k to the power 4, right? 1 minus k to the power 4, where k is the d inner upon d outer, right? D inner upon d outer, and d inner upon d outer is equal to here 0.5, 1 by 2. So this expression will be 1 minus k to the power 4 upon is will be equal to pi by 64 ds to the power 4. So they both will be cancelled out. Further we will simplify. Then what we are finding, ph is upon ps will be equal to d outer to the power 4, d outer to the power 4 1 minus k to the power 4, k is given 0.5, k is given 0.5 to the power 4 upon ds is given 0.866, right? D outer. So ds, in place of ds put the value 0.866 d outer, then it will be d outer to the power 4, right? Now calculate the value. When we will calculate it, simplify it, so what we see that d outer will be cancelled out, and finally this expression will be ph upon ps will be equal to 1.66, right? So p hollow is equal to 1.66 times of p solid. So what we finding? We are finding that buckling load for hollow column is 1.66 times higher, 66% higher than the buckling load for solid column, right? For the same, for the given condition, buckling load P hollow is PS plus 66% of PS, right? It is showing that when hollow columns have higher buckling load, higher capability of bearing the buckling load, right, in comparison to solid columns, right? Because here buckling load for hollow column is 60% higher, 66% higher than the solid column.